Next, we have 15.2, double integration over more general regions. In other words, not just rectangles. So, not just rectangles anymore. We really have two different kinds of approaches if we're still in Cartesian. We'll talk about polar in the next video, but for now, strictly Cartesian. When it comes to Cartesian, there's two approaches. We either have regions that are vertically simple or horizontally simple. Some regions can be both vertically and horizontally. Some regions can also be neither horizontally or vertically simple. But for the problems that you'll see, the region is best. There's usually one way that's best and one way that's clear. On the exam, you will not see a region that is neither vertically simple nor horizontally simple unless it is something that could be used in polar, like so radially simple. But for Cartesian, you're either going to have something that's both or one or the other. So really quickly, what is a vertically simple region? A vertically simple region effectively is a region where you can look at a top function and a bottom function. So you're effectively saying which function is above the other. So we're really focused here on the y direction. So which is above the other in the sense of above and below, meaning which has the larger y value, which has the lower or smaller y value. So for instance, an example here might be this kind of shape. So the area bounded between these two parabolas. This region in here, if we go ahead and call that, let's say this region is R, okay, or D, let's say D, since this is talking about D here, give it the same name. This region, D, is vertically simple. Why is it vertically simple? Because you can think of this whole surface as this curve, as the top curve, and this is the bottom curve. When you do left and right, so sort of more a horizontally simple method, it's a little bit more awkward because up here, if you think of left and right, you have the same curve for left and right, okay? And then right here, as soon as you move on the other side of this dotted line from this side to this side, now you have this curve. So what's the left curve changes on either side of this dotted line. But for vertically simple, it doesn't matter where you are, here, 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 or anywhere in between, this curve is always on top and this curve is always on the bottom. So whenever you're able to say this function is always above this other function and they never switch, that's the order that, generally speaking, you want to integrate in. So that's what we have here. So to match it up with this description here, we would say that these x values, where the region begins and ends, we're just saying what's the leftmost x value, what's the rightmost x value. But then, if we're at some arbitrary x value, x, so some x between a and b, what does y range between? Well, y ranges between whatever this y value is. And what is that y value? Well, it depends on what this lower curve is. So, according to this, I've called the lower one g1. So let's go ahead and call this y equals g1 of x. And this will be y equals g2 of x. So 1 is the lower, g2 is the upper. So at some arbitrary x value, the y value on this curve is given to us by this function, and then the y value on this upper curve is given by this function. So that's why y is sandwiched between two functions. So if you want to integrate this function, which we don't see, right? Everything we did here in this picture has to do with d. We didn't talk at all about the function we're actually integrating. Because when it comes to double integrals, the more time-consuming part of the process is learning how to describe what this d is and set it up that way. You don't actually need to sketch this function at all to figure out what your bounds are. You only need to sketch what d is. So you'll always have constants on the outside. And depending on what these are, you could have constants for these. It depends on what your region looks like. But in general, we allow for the possibility that they are functions. So the way I keep this straight is for vertically simple regions, we integrate with respect to the vertical variable. So the dy is first, so integrate with respect to y first. And also for vertically simple regions, we think about stacking or listing what's above the other in the vertical direction, which is the y direction. To contrast this with horizontally simple regions, a horizontally simple region might look something like, we could have something like, maybe I'll do sideways parabolas. Cheap, that's a cheap example, but it works. So very much in the same sense as up here, if I think about which function is on top, which function is on bottom, it's kind of awkward because over in this region, both the, for the top and bottom functions. For the top function, it's this curve, and for the bottom function, it's also this same curve. But what's worse is that on either side of this dotted line, you're going to switch which function you're saying is on top and which is on bottom. So this is kind of awkward to do. What's better is to interpret this region as horizontally simple, because if you strike any horizontal line in your region, just strike a line, doesn't matter where, the thing is that this has to work for any horizontal line that you strike. So if you strike a horizontal line through this region, you can see that there's a well-defined left curve and a well-defined right curve. So, in this case, we're defining the left curve as g1 of y. Notice here that the variable is y, so we're really actually solving this for x, and this rightmost curve is x equals g2 of y. And we're going to go ahead and say here that maybe I'll move my axis up a little bit, something like that. So then here, this is from C to D. So you just look at what's the smallest and largest y value. So you get your y constants, and then we're gonna solve for x for these two equations, and then report back what's the left curve, what's the right curve. So really, your goal for both vertically simple and horizontally simple is to come up with these two sets of inequalities. That's really what you want. First, look at first sketch your region. Then think about striking vertical or horizontal lines and see which scheme produces a well-defined top or bottom function, or a well-defined left and right function. If you ever find yourself saying, oh, well, it's left, there's a left function on this side, but as soon as we go to this height, we have to switch functions, that's probably an indication that you should reinterpret the region as, well, maybe vertically simple, the opposite of how you were interpreting it. Once you have that decided, whether you're going to choose vertically or horizontally simple, go ahead and come up with your two inequalities. Because once you have your inequalities written down, they immediately tell you what your bounds are. So for me, it's sketch, choose whether we want to do vertically or horizontally simple, come up with the inequalities, and set up the double integral. For regions that are both vertically simple and horizontally simple, you can set them up in either way, but one way might be easier than the other way. So just be aware of that. All right, the next topic that we have in 15.2 is volume between two surfaces. So the way I think about this is we're setting this up where our surfaces are stacked in the z direction. So we think of, when I say top and bottom, I'm really referring to what surface has the larger z value and which surface has the smaller z value. So earlier, a moment ago, when we were talking about x and y, top and bottom meant y direction. But now for this problem, we're switching gears a little bit, and I'm just trying to say, when I say top, I am talking about top and bottom. I'm referring to the ordering in the positive z-axis direction. So if we have two surfaces, two functions, z1 and z2, they're two surfaces, such that the z1 surface is below the z2 surface. For every z value in some domain D, where D is some domain, some subset of the plane, and in particular, it is the projection of the bounded region onto the xy plane. So let's go ahead and take a look at this visually to see what exactly I mean here. So for instance, we could consider having two paraboloids. So here, let's take a look at a graph here. So we've got a paraboloid, so something like z equals x squared plus y squared. So that's a paraboloid that's opening upward. And then let's turn that off for a second and think of another paraboloid. This time a paraboloid that's opening downward. So it's going to start at a z value of 4. So this in particular is z equals 4 minus x squared minus y squared. Okay. So if I graph both of them at the same time, then we can see that they do section off this region of space. Okay, so now what we can think about here is this surface right here, this one on top, this is the top surface. So this is sort of like our Z1 and Z2. So our Z2 is the top surface. So for this problem here, the Z equals 4 minus x squared minus y squared, that would be the top surface, and Z1 would be the bottom surface, which is Z equals x squared plus y squared. So when we say top and bottom, that's what we're referring to. We stack things in the Z direction, okay? So in the Z direction, this surface is above the other. So that's the region that we have. And now if we turn these off, I've also went ahead and created a solid region in the middle, so you can see where they overlap is some shape like that. So this is actually the shape that we want to go ahead and calculate the volume of. And the way that we're going to do this, once we have identified, which we've already done, which surface is the top surface, Z2, which surface is the bottom surface, Z1, we now know our Z inequality. We know exactly what that is. So now we want to know what region do we integrate over in the xy plane. So what we can do is actually shift our view directly from above. This image looks a little bit weird just because of the way things are being clipped, but really what we end up having here is a circle in the xy plane. What's the radius of this circle? Well, it's not 1, it's not 2, it's something in between that. How would we actually figure this out? So conceptually, what we're actually doing here is we're looking at the shape at its widest point, and we're projecting that widest cross-section down into the xy plane. Or if you want to think about it as the sun being directly above the z-axis, then this shape will cast a shadow on the xy plane. And that shape of that shadow would be, well, it's what's blocked out the most. What would be blocked out the most would be the widest cross-section of that shape. So this is the region of integration in the xy plane. So how do we figure this out using algebra instead of a visualization thing? So if we turn this off and go back to what we have here, effectively what you would do here for the case of this widest circle, actually, let's look back, plot 3D for a second here. Essentially, that widest circle, what does it result from? It's the result of these two surfaces intersecting. So for this particular region, to figure out our domain of integration in the xy plane, the domain D, we need to figure out what this curve of intersection is and then project that into the xy plane. So how do you find the intersection between two surfaces? You would set them equal and go from there. So looking back at what we have here in the overview, once you know which surface is above which, and a very similar idea to what you've done in Calc 2 for finding the area between two curves, you identify the top curve and the bottom curve, and then you do top minus bottom. Well, same thing here. Identify the top and bottom surface, do top surface minus bottom surface. That's what you'll integrate. And then what is your domain of integration? Well, that's found by, in the hypothetical example that we kind of looked at with the two oppositely opening paraboloids, we would set them equal, find that curve of intersection, which represents the widest cross-section of the solid region, and project that down into the xy plane. Once we have that in the xy plane, we can go ahead and interpret that region as either vertically or horizontally simple. And in a moment, we'll go to polar coordinates, and for this particular example of the two paraboloids, it would be best to do this in a radially simple manner using polar coordinates.